This recording covers section 6.6. The question in this section is what values of x will make a particular inequality true. We'll start with a simple example. The absolute value of x is greater than 4. Think in your head of some numbers that would make this statement true. You might be thinking of numbers that are greater than 4, numbers like 5, 6, 7. Or you may be thinking of numbers that are more negative than negative 4. -5, -6, -7. There are two different ways that this statement, the absolute value of x is greater than 4, could be true. The first is those numbers bigger than 4. In other words, x's that are greater than 4. The second is those numbers that are less than -4. X is less than -4. On a graph, you can see that these would be two separate rays extending in opposite directions. These can't both be true at the same time. Either x has to be greater than 4 or x has to be less than -4. But there's no overlap of these two graphs, and the two statements can't be true at the same time. So either one or the other has to be true. So the solution to the above inequality, the absolute value of x is greater than 4, is a compound statement. Either x is less than -4 or x is greater than 4. Next, we'll switch the inequality sign around. I want to know what values of x would make this statement true. The absolute value of x is less than 4. You might start thinking of numbers that are just a little bit smaller than 4. Numbers like 3, 2, 1. You might also be thinking of negative numbers that are a little bit bigger than -4. Numbers like -3, -2, and -1. In the first case, you're looking at x's that are less than 4. In the second, x's that are greater than -4. If we graph those two statements, the x is less than 4, shown here in green, shows all values of x that are smaller than 4 but not equal to 4. Shown in red are all the x's that are greater than -4. The overlap of these two things, the area where these two things are true at the same time, is the solution of the above inequality. X has to be greater than -4 and at the same time smaller than 4. Only those numbers between -4 and +4 will make the inequality true. Anything bigger than 4 is going to be too big. Anything smaller than -4 won't work either. So in this case, we join the two statements with an and. The solution to the inequality, the absolute value of x is less than 4, is x is greater than -4 and at the same time x is less than 4. A memory trick to help you remember when you join statements with an or and when you join statements with an and is this phrase Gorland. Here's the way it works. If you have an absolute value is greater than something, for example, the absolute value of x is greater than 4, the solutions will be joined with an or statement. If you have an absolute value is less than something, for example, the absolute value of x is less than 4, the solution will be joined by an and statement. I recommend at this point that you pause and go back and review the first two examples and keep this Gorland in your mind. Notice that when the absolute value of x was greater than 4, the solution was an or statement. When the absolute value of x was less than 4, the solution was an and statement. Let's work through a practice problem to see how to apply Gorland to find the solution to an absolute value inequality. In the problem below, I want to know what numbers can I plug in for m that make this inequality true. What values of m will make the following quantity, 3 times the absolute value of 5m minus 6 minus 8, be less than or equal to 13. Obviously, there are some numbers that it's okay to plug in for m and some numbers that won't work. And I want to understand what values of m is it okay to plug in. The first step is that I need to get the portion of the equation inside the absolute value bars, that absolute value chunk. I need to get that by itself on one side of the equation. So the first thing I'll do in this case is add 8 to both sides of the equation. I don't have to switch my inequality sign around. I didn't multiply or divide by a negative number. And so I get this simpler inequality. Next, I'll divide both sides of the inequality by 3. Again, I'm not dividing or multiplying by a negative number, so I don't have to switch my inequality around. Now I'm left with this expression. 5m minus 6, the absolute value of that, is less than or equal to 7. I have the absolute value chunk all by itself, so I'm done with step 1. This is where I have to apply the Gore-Land trick. In this case, we have the absolute value of 5m minus 6 is less than or equal to 7. We have the absolute value is less than something. That's the L part. So I'm going to split this into 2 AND statements. The first one, I'm going to take the stuff inside the absolute value bars, is less than or equal to 7. It looks like I just simply dropped the absolute value bars here. The second statement is a little bit more complicated. Here, I take 5m minus 6, stuff inside the absolute value bars, is greater than or equal to negative 7. A good way to think about it is that these two statements taken together show that 5m minus 6 has to be between negative 7 and 7. Notice that when I did this, the absolute value bars went away, and I have 2 separate statements that I can solve separately. We have these 2 inequalities joined by an AND. We just need to solve them one at a time. We'll start with the inequality on the left. To get m all by itself, first I'm going to add 6 to both sides of the inequality. That leaves 5m is less than or equal to 13. Then I'll divide both sides of the inequality by 5. It's a positive number, so I don't have to switch the inequality sign. And I get a resulting m is less than or equal to 13/5. Now I have to go solve the second inequality on the right. Here, I'll begin by adding 6 to both sides, which will result in 5m is greater than or equal to negative 1, and I'll divide both sides by 5 to get m is greater than or equal to negative 1/5. These 2 solutions are joined by an AND. What this means is that m has to be less than or equal to 13/5 and at the same time greater than or equal to negative 1/5. Another way of writing this is that m is between negative 1/5 and 13/5. This means that any value of m between negative 1/5 and 13/5 will make the original inequality true. Here's the original inequality, and I can plug in any value of m that's between negative 1/5 and 13/5, and the resulting inequality will be true.